Welcome to The Explainer. Today, we're diving into something that sounds super simple, but is actually a huge deal in AI vision. It's called zero padding, and it's basically the secret ingredient that helps our neural networks see things way, way more clearly.
But before we get into the solution, let's talk about the problem it solves. And it's a bit of a puzzle, really. Have you ever wondered what happens when you feed an image into a convolutional neural network? Well, a lot of the time, the image that comes out the other end is smaller. Why would it do that? What's going on there?
So you might think this is some kind of glitch, right? But nope, it's not a bug. It's actually a core part of how these networks see and process information. You can almost imagine it like a shrink ray that hits the image every single time it goes through another layer of the network.
Okay, so let's look at a classic example. This is from the MNIST dataset, which is kind of like the hello world for image recognition. We start with this little 28 by 28 pixel image of the number 7. Pretty standard stuff for training an AI.
But check this out. After just one pass through a filter, what we call a convolution, the image is already smaller. It's shrunk down to 26 by 26 pixels. A whole border of pixels just gone. Poof. So why? Why does this happen? What's the actual mechanism that's causing the image to shrink? Well, to figure that out, we got to peek under the hood and see exactly how the network's filter moves across the image.
All right, to make this super clear, let's simplify things a lot. Imagine we have a tiny 4x4 grid, and we're using a 3x3 filter to scan it. Now there's one really important rule. The filter has to fit completely on the grid. So the very first place it can go is right here, snug in the top left corner.
Okay, from there, it can scoot over one spot to the right. But that's it. It's hit a wall. If it tried to move any further, part of it would be hanging off the edge, and that's a big no-no.
So it can't go right anymore. The only other move it has is to shift down one row and start over from the far left again.
And then it makes one last slide over to the bottom right corner. And we're done. That's literally all the moves it can make. There are no other places for this 3x3 filter to go on our 4x4 grid. So what's the result of all this? Well, because the filter could only take 2 steps across and 2 steps down, it only created 4 new data points. We started with a 4x4 input, and we ended up with a 2x2 output. And there it is. The image has shrunk.
And for you math fans out there, there's actually a really clean formula for this. You take the input size n, subtract the filter size f, and add 1. That's how many steps you can take. So for our example, it was 4 minus 3 plus 1, which is 2. So we get a 2x2 output. The math works out perfectly.
Okay, so the image shrinks. Big deal, right? Well, actually, yeah, it is a big deal. This isn't just some weird little side effect. It causes 2 major problems for our AI.
Problem number 1, we are literally throwing away data. The pixels on the very edge of the image, they barely get looked at. And what if there's something important there? And problem 2 is even bigger. If you have a really deep network with lots of layers, the image shrinks so fast that after just a few steps, it can become a tiny, useless little blob.
So, how do we fix this? How can we get the network to look at the whole image without turning it into a postage stamp? The answer, thankfully, is super elegant and incredibly simple. It's a technique called zero padding, and it is exactly what it sounds like. We just add a border of pixels around the outside of the image, and we fill that border with zeros. That's it. We do this before the filter starts its work.
Okay, let's go back to our little 4x4 grid. But this time, let's wrap it in a nice, cozy border of zeros. Now our image is effectively a 6x6 grid. And look what that does. The filter can now sit perfectly centered on that original corner pixel. It has room to breathe.
Because of that extra space, our 3x3 filter can now move 4 times across and 4 times down. That gives us 16 spots, which creates a 4x4 output. That is the exact same size as the original image we started with. Boom, problem solved. Now, the best part is, you don't have to sit there with a calculator trying to figure out how many zeros to add. In practice, when you're building one of these networks, you just tell it what kind of padding you want, and it handles the rest.
And there are really 2 main flavors you'll see. The first is valid padding. That's a fancy way of saying no padding at all. This is the one that causes the shrinking, and it's usually the default. But the one we're interested in is same padding. This one is smart. It automatically adds just enough zeros to make sure the output is the same size as the input.
Okay, let's look at a real-world example. This is a model summary from Keras, which is a super popular tool for this stuff.
With valid padding, so no padding, you can see the output shape just gets smaller and smaller with each layer. We started 20 by 20, and just 3 layers later, we're down to a tiny 8 by 8 grid. Yikes!
But now, check this out. Same exact model, but this time we've turned on same padding. And would you look at that? 20 by 20, 20 by 20, 20 by 20. The dimensions are perfectly preserved all the way through. This means our network can be much deeper and learn way more complex stuff without losing track of where things are in the image.
So here's the main takeaway. It's kind of wild, right? By just adding a simple border of zeros, which have no actual information in them, we solve that whole shrinking problem. We get to keep all that valuable data from the edges, and we can build much, much deeper and more powerful AI vision models.
It might seem like a small trick, but this technique is absolutely fundamental to pretty much all modern computer vision. And it kind of makes you think, right? If adding a border of nothing is how we preserve an image's size, what other little choices, like how big the filter is or how far it jumps with each step, are shaping how an AI actually sees and understands the world around us?